We are now in the alkynes portion of Unit 4, and as with any new functional group that we study, we will be looking at the structure of the alkynes, the physical properties of the alkynes, how to name alkynes, the reactions that we will use to form the alkynes, and the reactions of the alkynes once we have formed them. This video will focus in on the structure of the alkynes and the physical properties of the alkynes. The alkyne functional group is a functional group containing the carbon-carbon triple bond. Here are two examples of naturally occurring compounds containing that carbon-carbon triple bond. Looking at the position of the triple bond within an alkyne, we can divide our alkynes into two classifications: the terminal alkyne or the internal alkyne. The terminal alkynes are those in which the triple bond is at the end of a molecule, while an internal alkyne has the triple bond somewhere other than the end. Recall from our Unit 2 discussion that a terminal alkyne will look different from an internal alkyne in both IR and proton NMR spectroscopy. In an IR spectrum, the terminal alkyne has a carbon-hydrogen bond in which the hydrogen is attached to an sp carbon, but an internal alkyne does not have a hydrogen attached to an sp hybridized carbon. So, in an IR spectrum, the terminal alkyne will have an absorption that shows up right around 3300 wave numbers to represent the carbon-hydrogen bond in which the carbon is sp hybridized. Also recall that the carbon-carbon triple bond of a terminal alkyne will have a more intense or a stronger signal in the IR spectrum than an internal alkyne, and that was due to the fact that the terminal alkyne is less symmetrical than the internal alkyne. This peak would show up at around 2200 wave number. In NMR spectroscopy, the hydrogen on the terminal alkyne will be found around 2.5 ppm, and this would be absent in the internal alkyne. Moving on to the structure of the alkyne, recall that the triple bond consists of 2 pi bonds and 1 sigma bond. Each carbon of the triple bond is sp hybridized, which makes it linear with bond angles of 180 degrees. Here is the orbital view of the bonding within the carbon-carbon triple bond. The sigma bond is formed by head-to-head overlap of the sp hybridized orbitals from each of the carbons, and the pi bonds, there's one pi bond there, and then another pi bond there. The 2 pi bonds are formed by side-to-side overlap of the unhybridized p orbitals. A comparison of the bond lengths and the bond strengths of the carbon-carbon triple bond compared to the carbon-carbon double bond or the carbon-carbon single bond shows us that the carbon-carbon triple bond is a shorter bond than the other two, as well as a stronger bond than the double or the single. But note that just as in the alkene, the strength of the carbon-carbon triple bond is not triple the strength of a carbon-carbon single bond, and that shows us that the pi bonds are weaker bonds than the sigma bond. So just as we saw in the alkene, the pi bonds of the alkyne will make the alkyne much more reactive than the alkane, and for most of the reactions, the reactivity will occur right at the pi bonds. When I want to draw 5 carbons in a row with the triple bond between carbons number 2 and 3, using the line angle formula, I will do it in the following way. That way you can clearly see the 5 carbons. 1, 2, 3, 4, and 5. Now sometimes my students do not draw linear bond angles between carbons 1 and 2 and 3 and 4, and they will draw the structure looking like this. And although that doesn't show the correct bond angles of the structure, I still understand what they're trying to represent, so I do accept that type of drawing. But be very careful, because I've also seen students try to draw the structure like this. Now, the problem that I have with this representation is that, to me, instead of having 5 carbons, I see 7 carbons. 1, 2, 3, 4, 5, 6, 7, with the triple bond between carbons 3 and 4. So if you want to draw the alkyne structure with non-linear bond angles, just make sure that the triple bond extends all the way to the 2 carbons so that it's not ambiguous, leaving me thinking that there are extra carbons in your structure. The physical properties of the alkynes are similar to the alkanes and alkenes because they are all nonpolar molecules, so they have relatively low boiling points and melting points, and they are not soluble in water. In general, alkynes will follow the same trends that we see for the alkanes and the alkenes, where the boiling points will increase with the number of carbons and decrease with the branching. I do, however, want to point out an anomaly of this alkyne right here, which is a 4-carbon alkyne, and with the triple bond between carbons number 2 and 3. Now, this alkyne, if you look at its melting point and its boiling point, has a melting point and a boiling point significantly higher than the alkenes, or even this terminal alkyne that has the same number of carbons. So here, these all have 4 carbons, and the melting points of these 3 here are all negative 100 something degrees Celsius, but this one's only negative 32. So yes, it's still a very low melting point, but significantly higher than the other 3 examples. Now that has to do with the linear structure of this alkyne. Since the entire molecule is linear, these molecules can pack together much more easily, and that makes it harder to melt, and thus the higher melting point. As for the acidity of the alkynes, terminal alkynes are much more acidic than alkanes or alkenes. You can look at the pKa values for an alkane, which is around 60, and compare that to an alkene, which is in the mid-40s. Well, a terminal alkyne has a pKa right around 25. Also note that although this makes the terminal alkyne much more acidic than the other hydrocarbons, It is by no means a strong acid, and by comparison, you can compare the pKa of a terminal alkyne with a pKa of a typical carboxylic acid, which has a pKa around 5. Why are terminal alkynes more acidic than other hydrocarbons? It has to do with the percentage of S character. Recall that an sp orbital has 50% S character, while as an sp2 orbital has about 33 1/3% S character, and an sp3 hybridized orbital has only 25% S character. The larger percentage of S character means that the electrons in an sp orbital, like we have for the terminal alkyne, those electrons will be held closer to the nucleus, so the negative charge is better stabilized. A more stabilized negative charge is a weaker base, thus making the conjugate acid a stronger acid. Because sp hybridized carbon-hydrogen bonds are more acidic than sp2 or sp3 hybridized carbon-hydrogen bonds, this means that our terminal alkynes can be more readily deprotonated with a strong base. Note I said terminal alkynes because an internal alkyne, although it does have an sp hybridized carbon, will not have a hydrogen on that sp hybridized carbon, so it cannot be deprotonated as easily with a strong base. When a terminal alkyne is deprotonated by using a strong base, the resulting anion that is formed we call the acetylide anion, and this anion is synthetically useful because it can act as either a very good nucleophile or a very strong base. To determine how strong of a base is needed to deprotonate a terminal alkyne, we must consider its pKa. The terminal alkyne's pKa is about 25. So for a base to be strong enough to pull off that proton, it must be a base whose conjugate acid is larger than that of the terminal alkyne. NaNH2 or NaH are two common examples of bases that are used to deprotonate a terminal alkyne. Remember that in an acid-base equilibrium, the equilibrium favors going toward the weaker side. So if a base like sodium hydroxide is used instead, so we'll take hydroxide, and I'll put that here as my base. That means that the conjugate acid that is formed is water. Now, the pKa of water is right around 16. So you can see that water is a stronger acid than the terminal alkyne. Because of that, using a base like sodium hydroxide would have this side of the equilibrium being the weaker side, and because it's the weaker side, the equilibrium would favor going toward that side, and the alkyne would exist as the alkyne rather than as the acetylide ion. In contrast, if you change the base to NaNH2, now the conjugate acid is NH3, and we saw that the conjugate acid had a pKa around 38. So this makes NH3 a weaker acid than the terminal alkyne, and the equilibrium will be product favored, meaning that NaNH2 is a strong enough base to give us the acetylide ion. This also demonstrates why the alkenes and the alkanes cannot be easily converted into their conjugate bases. That's because even a strong base like NaNH2 would not be strong enough to deprotonate an acid like an alkene, which has a pKa around 44, or an alkane, whose pKa is around 60.